breakout session K because of the COVID-19.
都是线上参会，那么跟去年
attended meeting virtually. This year,
他们也采用的是线上，
COVID-19, some of the Chinese speakers even joined us online. And our topic today is a risk assessment of combined.
现场，那么他们也通过我们的这个
And
网上
some audience also joined us through.
刚才我们的会务已经告诉我们第一位演讲的
The first speaker
专家已经在线上了。
is already ready for the presentation.
安全局科学委员会的Jane Law 博士。
He is Jin Law Dong,
Jane 博士来给我们
Senior Scientific Officer, the Scientific Unit, European Food Safety Authority.
Hello.
OK Hello.
Hello. Good morning. This is Jean-Loup Don from EFSA.
OK
can you hear me?
Dr. Jin, yeah, we can hear you, and please you can begin. Thank
Okay,
you.
thank you. Thank you very much.
30 minutes. OK.
Good morning, everyone. I'm very pleased to be here this morning. I hope you can all hear me okay. I would like to talk to you this morning about the risk assessment of combined exposure to multiple chemicals at EFSA and provide you with a horizontal perspective. First of all, EFSA published a guidance in 2019. Guidance on harmonized methodologies for human health, animal health, and ecological risk assessment of combined exposure to multiple chemicals. This guidance deals with risk assessment of, so to speak, chemical mixtures or combined exposure to multiple chemicals, looking at whole mixture approach or component-based approach, but also with methodologies on how to deal with interactions. The guidance is structured from the problem formulation level to the exposure and hazard assessment, all the way to risk characterization. Finally, the guidance contains reporting table with examples on how to perform a human health risk assessment, an animal health risk assessment, and an environmental risk assessment. Just to show you briefly the harmonized framework, again, you have your problem formulation, you have your exposure assessment, your hazard assessment, and your risk characterization. And of course, we need to consider factors influencing each of those steps, such as the assessment sequence, the use of dose addition as the default model, and how would we bridge data gaps when data availability is low. Another important aspect are the tiering principles. And here we note that at low tier, when we have little data to perform the risk assessment, we may use a conservative approach and have a, let's say, simple risk assessment performed. On the contrary, when we have a lot more data, which the risk assessment becomes more complex, we would of course increase the accuracy and decrease the uncertainty. Briefly. So let's look at the problem formulation.
詹博士，请用翻译模式。您的 PPT 请用翻译模式。
Sorry, the
OK.
Please,
PPT on showing mode.
please use the presenting mode of your slide.
My apologies.
Full screen. Thank you.
Display setting. It is not in full mode.
Not that. It's speaker mode.
Please shift it to speaker mode, full screen.
Okay, is this in the taskbar? Speaker mode.
Display, no, 不是这个。
My apologies for that.
Display.
Yeah,
Second button. In this displaying setting, second button. Yeah.
In the display setting.
Yes. This. Yeah. Okay. This way. Yeah.
Okay. Apologies. So the problem formulation.
Okay.
The problem formulation. We have a display. We have a risk assessment question, which may be dealing with human risk assessment, farm animals, companion animals, environmental species of environmental relevance of the ecosystem. So the first step is, of course, what the species to assess and the multiple chemicals we are dealing with. Then how do we deal with the risk assessment, with this question for risk assessment, and of course a plan to perform the risk assessment. So the first step, you would describe the mixture, characterization of the composition of the mixture, availability for the components or for the whole mixture if we don't have knowledge about all the components, and is co-exposure and co-effect likely, and that is the gatekeeper step. Of course, if no, we stop. We then have a conceptual model where again the question is formulated, the source of the chemical, the exposure pathways, the species, the subpopulation, and the regulatory framework are defined. We look at the methodological approach, and then we have, of course, the analysis plan, and we then initiate with the risk assessment. Of course, this can be updated, modified in an iterative manner. When it comes to exposure assessment, we have, of course, as exposure is the combination of occurrence data and consumption data. We have the amount of each chemical in food, how much food is consumed, and the combination of together to get the exposure estimates. And as we discussed earlier on, we have a tiered approach depending on the data we have, going from a tier 0, for which we may have default values, all the way to individual co-occurrence data and individual consumption data. Hazard assessment, same concept, stepwise approach. The first example here is looking at component-based approach, for which we have all the components in the mixture. Let's say a group of pesticides. The first thing is confirming the components of the assessment group. What are the individual chemicals? And the criteria for grouping is, are we grouping using a hazard, for example, toxicity, let's say liver toxicity. So how toxic is each chemical in the mixture? We collect the toxicity values for each chemical, and we have to answer the question whether do they interact or not, and do they become more toxic together. So we collect the available hazard information. We looked at the evidence for combined toxicity. We would use dose addition as the default, but if there is evidence for interaction, then we would look at such evidence. We then have the hazard characterization, and we summarize the hazard data for each component of the assessment group. Risk characterization, of course, here we will summarize the exposure data and the hazard data, as illustrated before. So we combine both for all the chemicals to derive the risk value. We then confirm or revise the approach we define in the problem formulation for the risk characterization. We may start using tiering principles with a fit-for-purpose methodology based on problem formulation and available data. We then can summarize the risk characterization results and interpret the the risk characterization metric. Of course, can we identify a health or an environmental concern? If no, we would stop. If yes, what is next? We either refine the approach using a more complex approach, if we've used a very conservative approach, or we would discuss with risk manager to reduce the exposure. This is the reporting table. Again, you have the problem formulation, exposure assessment, hazard assessment, risk characterization, with all the different elements within each framework. And here are a couple of examples of technical reports from this guidance document, looking at human risk assessment of multiple chemicals using component-based approach, but also animal health risk assessment of multiple chemicals in essential oils for farm animals. So here we present the application of the document in the field of human risk assessment and animal health risk assessment. I just wanted to highlight to you, of course, some toxicological and exposure tools. We have the EFSA hazard database, which is published, and you can download it in Excel, associated with a review article in Environment International, but also a review of all the available open access exposure tools, again, from colleagues in the data unit, also published open access. So if you want to test the guidance document using available data, then these are sources of data. Wanted to highlight a little example on also looking at relevant examples of mixtures in food safety, occurrence and co-occurrence of mycotoxins in cereal-based feed and food, resulting from a project we had together with a number of universities, University of Parma, University of Portugal, University of Piacenza, and colleagues in Ireland, where we looked at co-occurrence and consumption pattern for mycotoxins and cereals, looking at hazard data for each of those mycotoxins using the open food tox I just mentioned, and performing the risk characterization using the combined marginal exposure. A second document that we're currently finalizing is the one on scientific criteria for grouping chemicals into assessment groups for human risk assessment. So just briefly, we received a request a couple of years ago to develop a scientific opinion on criteria to group chemicals for human risk assessment of mixtures. So the key is to set the cumulative assessment groups for the human risk assessment of pesticides as requested by the European Commission at DG Sante. This is, of course, relevant to contaminants for grouping chemicals such as perfluoroalkyls, brominated flame retardants, and so on. To the FEEDAP, of course, looking at again, these essential oils or botanicals, but also to the flavoring, the food flavoring panel for smoke flavorings and grouping. And here we can include chemical properties, structure, class, functional group, and use the ECHA read across guidance document and potentially the OECD QSAR toolbox. Of course, this provides overall support to all panels dealing with chemical risk assessment. If you look at the terms of reference, the scientific opinion, again guidance document, scientific principles and relevant cross-cutting guidance would need to be taken into account, such as the weight of evidence or uncertainty analysis. What is the context of the risk assessment? Priorities, urgent, pre or post-market, tiering and fit-for-purpose scenarios, considering available data, as presented earlier on, prioritization approaches, risk-based and exposure-driven. How can we prioritize the chemicals we're dealing with? Relevant EFSA areas and international activities, of course, always try to harmonize and avoid duplication. And the document is then published for public consultation, as we do for all the guidance documents of EFSA. The content of the document have an introduction, general principles, the hazard-driven criteria, prioritization methods, recommendations, and a number of annexes which explain, for example, how to group the chemicals using hazard-driven criteria, applying the weight of evidence methodology, and a couple of examples on how to apply the prioritization methods to group pesticides using risk metrics for single chemicals, and how to group contaminants in breast milk using exposure-driven approaches. So this document has been published in May this year, 2021. Again, we had the hazard-based criteria, prioritization recommendation. Last week, we had an international workshop to discuss the guidance document. It was planned in 2020, but was delayed because of the COVID pandemic. And we currently are finalizing the document after taking into account comments from the public consultation as well as during the workshop. So just to give you a little detail, here we are looking at, of course, for the hazard-based criteria, the mode of action in the adverse pathways. And here you can see the difference between mode of action and adverse outcome pathways. Of course, the toxicokinetic dimension is the entire part of the mode of action, whereas the adverse outcome pathway starts at the molecular initiating event when the chemical has an interaction with its target. This is an important aspect because we may have different types of elements. And here is the hazard-driven criteria for grouping chemicals into assessment groups. It is a top-down hierarchical process where we would like to, we start, of course, with chemicals under consideration, defining the terms of reference, and passing the gatekeeper step. If there is co-exposure or co-effect that is likely. The gold standard, of course, is the mechanistic understanding, so common mode of action or adverse outcome pathway for grouping these chemicals into an assessment groups. We then move to a common, if we don't have this type of knowledge, we then move to a common toxicological effect or adverse outcome. And if not, we may look at common target organ system. Finally, if we don't have this type of data, we may group using in silico or structural information. Looking at an example here, acetylcholinesterase inhibition, we have a number of elements and a number of mechanisms. For example, we have this hypothyroidism, the functional alteration of the division of the nervous system of craniofacial malformations. Just to give you an example. When we're looking at the prioritization methodologies, we have a couple of starting points which may differ. The first one is you have your assessment group, which was defined from your hazard criteria. The second one could be I have chemical consideration defined in the terms of reference, passing the gatekeeper step, but I may have a very large group, or I may have to look at chemical contaminants in breast milk. So one way to prioritize the chemicals is first to look at, do I have the hazard metrics for the common effect of the organ system? If yes, I can look at the combined risk matrix and determine what is the relative contribution of each chemical to the combined risk of the group. And here we may use a predefined threshold, for example, 10% of an acceptable daily intake. And if yes, we may prioritize the chemicals. If we are below this predefined threshold, we may consider the chemicals as a low priority. If we don't have such data, we may use the hazard metrics for the critical effect. And here we will determine the risk metrics for the single chemicals look at the contribution of the chemical to the single chemical risk, again using a predefined threshold. If we don't have toxicological data or hazard metrics, we would use exposure-driven approach and look at the probability of co-exposure, and we may define a predefined threshold as well. And in this context, chemicals may be excluded from the grouping. Then all the chemicals that are identified as high priority could be placed into a final assessment group, or we could even the grouping using, again hazard-driven criteria. Just wanted to mention the metabolic interactions and combined toxicity. Mixture toxicity, of course, can involve interaction. We need to check if these interactions occur at current exposure level, are they relevant, and integrate such understanding in risk characterization. We may use an extra uncertainty factor, or we may look at the modeling of this interaction based models. And here you have an example where a chemical A may interact with a chemical B through either an inhibition or an induction of metabolism at the toxicogenic level, which may influence the combined toxicity and result either in potentiation and synergism mechanism, depending on whether the chemical is excreted, metabolized, either bioactivated by metabolism, production of a toxic moiety, or detoxified. And we can integrate the nature of such interaction in risk assessment. Just a couple of examples. We've looked at the Bayesian meta-analysis to quantify inhibition and induction of CYP3A4 metabolism in humans. We find certain factors for this risk assessment. And this was looking at grapefruit juice and St. John's wort from clinical trials to determine magnitude of interactions. And here is another example on investigating the interaction between melamine and cyanuric acid using a physiological-based toxicokinetic model in the rainbow trap. So that is a biologically based model. Another aspect of interactions here, some examples on looking at interactions and synergism in disease. We know that they are mostly due to inhibition of cytochrome P450 metabolism. Meta-analysis looking at the available data, where we can determine for acute toxicity, contact toxicity, magnitude of interactions. We have little data on oral.
Dr. Jane, we can hear you. Hello? 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 Dr. Jane?没有说话还是掉线了是吧？那么我们一般情况下怎么处理这种情况呢？好的，那现在可能只能这样了，因为
Speaker.
因为这个网络线上
Because of our connection, so we'd like to move on with next speaker. Our next speaker is from BFR from Germany, Mr. Glenn Lorman. Dr. Glenn Lorman will speak, will play a video, so I believe we will stay connected all the way.
好，那么我们现在就是还是我的意思就是说呢，待会儿我们放视频的过程中的话，那个第一个讲会。
Welcome to my presentation.
Okay.
My name is Glenn Lerman. I'm from the German Federal Institute for Risk Assessment, also known as the BFR. And today I'm going to use this opportunity to talk to you about the tiered approach that is currently used within the EU for risk assessment of combined exposure to multiple pesticides. And this is current practice for both plant protection products and for biocidal products. Question number one, to begin with, why do we even need a cumulative risk assessment? Well, as I'm sure you're aware, we have our biocidal product or our plant protection product, and that is made up of a mixture. Firstly and foremost, we have our active substance, or in very many cases, we have safeners, we have synergists, potentially, and also various co-formulants such as surfactants, dispersants, solvents, and so on. Now, in Germany, there are currently 1,785 plant protection products that are authorized. Each one of them, as I say, is a mixture, and it would be impossible then to test every one of these mixtures for their toxicological properties. So that is the reason then why we need a cumulative assessment for these products, mixtures, and we need to be able to assess them, and we can't do this by testing each and every formulation. As a regulator working within a regulatory framework, there is obviously also a regulatory requirement for taking cumulative effects into account. For plant protection products, we have to consider the active substances, safeners, synergists, and co-formulants within a product. And we have to take into account, as highlighted here, the cumulative and synergistic effects, not only of the product, but also of the residues, and that is also codified in the maximum residue levels, or MRL regulation, as you can see here. And obviously this is also valid for the biocidal products, where we also have to evaluate and consider cumulative effects from the use of biocidal products containing the same or different active substances. For us as regulators, the most relevant reference at the moment is the Guidance on Biocidal Products Regulation, Volume 3, version 2.1 from 2017, and in section 4.4.1 of this document we find our tiered approach to the cumulative risk assessment. That's what you can see here. We have three different tiers: tier 1, tier 2, and then tier 3 is divided up into tier 3A, B, and C. And what I'd like to do with you now is quickly look at the theory of these different tiers, explain that to you, and then the majority of the presentation will work through this using an actual case study so that you get a feel for how this is actually applied, how the cumulative risk assessment is done. So we begin at tier 1 by looking at the hazard quotient. And the hazard quotient is the internal exposure divided by, compared with, the acceptable exposure level. For biocides, we simply have the AEL. We can have a short, middle, or long-term AEL. If we're talking about plant protection products, then we could be talking about an AOEL, acceptable operator exposure level, or an ADI, acceptable daily intake, or an acute reference dose. If this is below 1, then it's acceptable. The product can be authorized. If it is above 1, this is not acceptable for us, and the product will not be authorized. And this is current standard practice for all products, both biocidal and for the plant protection products. For the plant protection products, we have the EFSA calculator. Here's a reference to that. Again, standard practice, so nothing new there. Now, in Tier 2, looking at the hazard index, now we're getting into the actual cumulative risk assessment. And here we now combine our hazard quotients for all the substances, the active substances, safeness that we have calculated already in Tier 1. We take the sum of those and we compare them to a reference. The reference is typically 1 if we assume there are no synergistic effects. And if we compare the sum of the hazard quotients to our reference, 100%. If it's below this, we're happy, product can be authorized. If it's above this, then we're not happy, and so we have to continue on to further refinement, which is then Tier 3. Tier 3A, this is where refinement of the risk assessment really takes place. And as I mentioned before, this can be divided up into A, B, and C, each of which we'll look at. In Tier 3A, we group the hazard indices according to the target organ. So what does that mean practically? If we have three active substances in our product, two of them and only one affects the kidney, then we only need to group the 2 that affect the liver, and the active substance not affect the liver, rather the kidney, can then be left out of the summation of the hazard quotients. And we compare this then to a reference, once again 1, unless we're able to account for synergistic effects. And it is below 100%, we're happy. If it's above, once again, we're not happy, and we have to go into Tier 3E, further refinement of our risk assessment. And here we now determine an adjusted hazard index according to the target organ. What exactly does this mean? We're able to then look at each of the active substances, for example, the 2 that affect the liver, and we can derive a reference value specific to that organ, in this case the liver. And using that information, it may be possible to refine the reference value. Once again, and we compare that to a reference. The reference again is 1, unless we can count for synergistic effects. And using our adjusted hazard index according to the target organ, if it's below the reference, we're happy. If it's above, we need to refine. Once again, we move to Tier 3C. Tier 3C is the final refinement in our cumulative risk assessment. Here we're interested in the mechanism of action of all the substances which affect the same target organ, for example, the liver. If we know from information which may be available that 2 substances, despite both affecting the liver, the same target organ, do this via different mechanisms of action, then we can assume there will be no dose addition, and so a cumulative is no longer necessary. We revert back then to the hazard quotients in Tier 1. If, however, we have a product with, for example, 3 active substances, and we find that only 2 of them actually affect the same target organ via the same mechanism of action, then we can leave the third out of the cumulative risk assessment and then reduce potentially the hazard index further, so that it may then be below the reference hazard index. If that's the case, then authorization can proceed. If that's not the case, if it's still too high, well then the product won't be authorized. So what I've told you so far is all very theoretical, and without actually having an example, I imagine it must be very difficult to follow what I've just told you. So that's why I'm going to spend most of the rest of the time that I have here working through an example with you. It's an example we recently had to do a cumulative risk assessment for the sake of confidentiality. I'll call it product X. Once again, it was a plant protection product. Yeah, so we'll look at the data and how we do a cumulative in practical terms now. So starting at tier 1, again this is standard practice at the moment for all products. This product had two substances, substance A and B, you can see in the top line of the table here, and we used the CIFSQ calculator because it's a plant protection product to calculate the exposure, the hazard quotient, and this here just shows you the input data that's put for calculating the potential to operators, workers, bystanders, residents, and so on. So tier 1, once again, we then have our results here in the two columns on the right, the hazard quotient calculated for substance A and substance B. And tier 1, we just look at each of these individually, and what we can see working down from the left, we have the operator model, the potential exposure, long-term systemic exposure for substance A is acceptable, for substance B it's not. So we have to then use some PPE, personal protection equipment, and then we can see for the operator that it's acceptable for both substance A and substance B. Then workers, looking at the potential exposure here. Once again, for both substances, it's too high. It's above 1 or above 100%. So we have to give them some PPE, some working clothing already is enough. That reduces it to an acceptable level. It reduces the potential exposure even further. We also need to consider residents and adults. Here all the values are green, so in that respect everything is okay. Normally, previously we'd say okay, tier 1 hazard quotient is below 1 for both substances, so we're happy with this. Perfect. Authorization is okay here. However, as mentioned on slide 3, we have to account for cumulative and synergistic effects. And using the framework that we have, this cumulative risk assessment, we now sum the hazard quotients for substance A and B, and that's what you can see there in the very right hand column, the hazard index, the sum of the two hazard quotients, and we now see that once again the potential exposure for the operator is too high. Give them some gloves, some PPE, and then everything's okay. However, we have now problems for the worker because we can see that even if the worker has the clothing on and the gloves, that the hazard index is above 1. And also for the children, for all potential exposure pathways, we also have a problem here because this is above 1. So using this cumulative risk assessment, we see that the hazard index was now above 1. So this is not good for the authorization. So we have to proceed to refinement, tier 3. Tier 3A. Now we're refining firstly by grouping according to the target organ. So we know from the assessment reports for both the substances the following information. Substance A had a very low AOEL, acceptable operator exposure level, 0.0032 milligrams per kilogram body weight per day. This was derived from a 1-year dog study and was based on reduced body weight. We also know from the assessment report that additional effects were also seen on body weight, organ weights, blood parameters at similar doses in the long-term studies on rats and mice. So not only dogs do we see reduced body weight, we also see effects at similar doses in rats and mice. For substance B, the AOEL was a lot higher, 0.15 milligrams per kilogram body weight per day. This was derived from a 90-day dog study and was based on increased relative liver weight and decreased body weight. So the question we ask ourselves here is, what are the common target organs, if indeed there are any common target organs, so that we can group them? At this point, we need to start digging into the assessment reports for each of the substances and information that we have with regards to toxicological effects. This is what we have here, substance A and substance B. And you can see, firstly, point 1, the critical effect for the reference value was the body weight, as mentioned before from the 1-year dog study, whereas in substance B it was the liver that was affected. So if we look at the target organs now, we can see that there were indeed effects on the liver by substance A. Similarly, substance B. We also had effects on the kidneys for both substances. Substance A, there was an effect on follicular cell hyperplasia with relatively no NOAEL. Nothing for substance B. You can see substance A, there were quite a few effects. There were effects on the GI tract, erythrocytes, etc. These were not seen for substance B. Developmental effects were seen for substance B, but not for substance A, and so on. And so basically what we can conclude from all of this is that there were two target organs that were shared by substance A and B, two in common, and these were the liver and the kidney. So theoretically, if we had two active substances which didn't have any common organs, then we would be happy with just looking at the hazard quotient. But now, because we have grouping according to the liver and the kidney, we then have to look at the sum of this. The hazard quotients themselves don't actually change. We have one for the liver, as you can see here, they're still the same values, and as a consequence, the hazard index remains the same. It's still problematic. It's still above 1 for the worker and for the child. So grouping simply according to the target organ didn't help with the liver, and obviously it's not going to help with the kidney either. Here, once again, we have the same values for the kidney. So using a grouping approach simply like this doesn't help refining. So we now have to move on to Tier 3B. Tier 3B, this is where we now adjust our reference values according to the target organ. As we have just established, both substances A and B both affect the liver and the kidneys. So what we need to do now is go back through our studies in the assessment report, and we need to adjust the AOEL, if possible, for the effects seen in the liver, and adjust for the effects seen in the kidney. To do this, obviously, we have to go back through all the relevant studies and see exactly at what concentration, what dose the toxic effects occurred. So now we really have some work to do. In Tier 3B, we now want to derive specific reference value. For this case, product X, we need an AOEL, and for that we typically look at the short-term studies. So I've listed here the different studies, 14-day mouse, 28-day mouse, etc., for substance A and substance B. And we look in each of these studies and we see at what dose an adverse effect in the target organ, the liver here, occurs. And so, for example, in the 14-day mouse study at the top left there, the adverse effects occur at a dose less than 5 milligrams. In the 28-day study, it's now 43 milligrams, and so on. I've highlighted in bold here the 1-year dog study, the lowest dose at which adverse effects in the liver were seen, 1.6 milligrams. We then use this as a point of departure for deriving our organ-specific AOEL. We correct for the oral absorption, 79%, uncertainty factor of 100, and that leaves us with a new refined organ-specific AOEL of 0.013 milligrams for the liver, which is a lot higher than the 0.0032 milligrams. For substance B, however, we know already that the liver effects were the critical effects in the 90-day dog study for deriving the original AOEL. And you can see that in bold here, 15 milligrams per kilogram per day. And so there is no possibility to refine the AOEL for substance B. Regardless, we now take these two values, one refined, one not refined, and plug them into the EFSA calculator. Here, once again, we use the EFSA calculator, but as you can see marked in red, the AOEL for substance A is no longer 0.0032, rather 0.013. For substance B, again, no refinement was possible, so that remains the same. And tier 3B then, grouping according to the liver, an adjusted value for the liver, what we find now is that if we sum the adjusted hazard quotients for the liver for substance A and substance B, the potential exposure is still above 1. However, again, if we use some PPE, then we are back in the green, and that's fine. For the worker, again, the potential exposure is above 1, but now if we give them some PPE, some working clothing and some gloves, we see that everything's okay. And again, for the child, the problem here was all pathways. You can see that here it's green. So for the liver, using this adjusted reference value, NOAEL, AOEL for substance A, this refinement has allowed us then to get our adjusted hazard index for the liver below 1, and with that it can then be authorized. So continuing now to the kidney effects, again we're still tier 3B, but we have to consider each organ separately. It's an AOEL, so we've got the short-term studies again, substance A and substance B. We go through each of these studies and we see at what dose these effects in the kidney, adverse effects in the kidney, occurred. And once again, for substance A, down the bottom, the 1-year dog study is the most relevant. The same dose, 1.6 milligrams per kilogram body weight per day, is where we start seeing effects in the renal proximal tubular epithelium. And again, we use this value corrected for the oral absorption as the point of departure for deriving the kidney specific AOEL, which is effectively the same as the liver AOEL, 0.013 milligrams per kilogram. Now, substance B, if we look at the 90-day rat study, what we find here is that the effects occur at 23.2 milligrams per kilogram body weight per day. That's the lowest dose at which we see kidney effects. And so we are able to refine the AOEL for the kidney based on this 90-day rat study. Again, correcting for oral absorption, but here it's 100%. Uncertainty factor of 100. And so we come up with a value of 0.23 milligrams per kilogram body weight per day. So now we have a refined AOEL for both substance A and substance B with regards to the kidney. So we take our refined AOELs and we feed them once again into the CIFSQ calculator. You can see here marked in red that I've put these new values into the CIFSQ calculator. For substance A, 0.013, for substance B, 0.23. All the rest of the data stays the same, and we do our calculations. And these are the results of the calculations. You can see for substance A and for substance B that the kidney effects were not a problem in and of themselves, only for the worker, the potential exposure, but as soon as we give the worker some clothing and some gloves, then everything is okay. However, we have to add these, once again, cumulative, to get our hazard index for the adjusted for the kidney. And you can see that the potential exposure for the operator is above 1, but again, some personal protection equipment reduces this below 1. Excellent. For the worker, again, the potential exposure is above 1, but if we give them some clothing and some gloves, everything is green again. And the same goes for the resident child and the resident adult. Everything's green, so everything's below 1, so we're happy and the product can be authorized. Both the liver and the kidney hazard indexes adjusted are below 1. Again, the product can now be authorized. So in the case of product X, there was no further tier 3C refinement necessary. It could be authorized based on the target organ specific reference values we derived. To date, in Germany at least, we have never had to do a tier 3C cumulative risk assessment. That said, however, applicants are submitting more and more mechanistic data, so I think it's a matter of time until we have to start doing these. I think this is something that's on the horizon. As I explained earlier, here we simply look at the mechanism of action of each of the different substances which affect the same organ. If it's possible to exclude different mechanisms, then it's possible to exclude the substances from the cumulative risk assessment. If, however, they do share the same mechanism of action, then obviously they still have to be grouped in the cumulative risk assessment. And so, in summary, we have our cumulative risk assessment approach with its 3 tiers. Tier 1, we look at the hazard quotients for each of the individual active substances. This, as I said, is already standard practice. Tier 2 is simple addition of the hazard quotients to give the hazard index. Tier 3A, this is now where the refinement comes in. Here we can group initially according to the target organ. Tier 3B, it is then possible to derive organ-specific reference values. And in Tier 3C, this is more theoretical than anything, here we can look at the mode of action and then by exclude substances affecting the same target organ if they have different mechanisms of action. And with that, we have now reached the end of my presentation. It is not possible, as I've mentioned at the very beginning, to test every mixture. In addition to that, we have legal requirements in the EU to account for cumulative assessment. So I hope that I was able here to demonstrate, show you how we currently undertake a cumulative assessment using this tiered approach. This is current practice within the EU. The way I have shown it today, the way I've demonstrated it, I will admit is we're only accounting for purely additive effects. I have mentioned that it can be used for synergistic effects, but here then we need more information, we need more data. And to be honest, I've not come across such data yet, so I've not yet been able to use it for synergistic effects. And yeah, with that, thank you very much for your interest. And yeah, I hope you enjoyed my presentation. Finally, I'd just like to offer my sincerest apologies for not being able to give my presentation live. However, if anybody has questions, I'm happy to do my best to answer them. You can just send me an email at the address there, and I'll do my best to get back to you. Thank you.
好了，刚才我们会务通知我那个第一个演讲的那个 Dr.
Speaker
Jane 已经在
Dr. Jane is back online.
请他来继续
We would like to invite Dr.
进
Jane
行第三位演讲者的报告。
and before after that we'll move on with the third speaker.
Dr. Jane.
Oh, yes.
Please continue your presentation.
Yes, thank you. I will share my screen. And I will put it. So. Okay, is it showing?
Yes.
Okay. Okay, so I'd like to go back to, I apologize, I've been a problem with the internet. And I'd like to go back to the experience we've had with pesticides residues in EFSA. So we have done quite a lot of methodological development in EFSA, as Glenn presented for the pesticides. This is the way in EFSA we've developed the methodologies for cumulative assessment groups, opinion on dissimilar mode of action, guidance for probabilistic exposure assessment, and a tiered methodology for the cumulative risk assessment. A lot of data collection, and of course, retrospective cumulative risk assessment with a pilot project looking at effects on the thyroid and the nervous system, and chronic acetylcholinesterase inhibition and craniofacial formation. So basically, the retrospective risk assessment was looking at a pilot assessment, looking at target organs, so thyroid and nervous system, monitoring data, and then looking at 10 groups in total. In 2020, a follow-up assessment looking again at target organ for the nervous system, this time chronic, since in 2019 we looked at acute effect, and again monitoring data from 2016, 2017, and 2018, and looking at population subgroups, 10 in total, adults, children, and toddler. So in this slide, you can see the actual reports that have been published on EFSA website. And I'm trying to get to the full screen, but the button is not okay. Then from these reports, we had a number of prioritization methodologies that have been developed. From the ones I've presented earlier on. So we're looking at open food tox, taking the toxicological data, monitoring data, screening the risk for individual pesticides, identifying high priority substances, screen the risk per organ, high priority organs, and then produce cumulative assessment groups for those specific effects. So looking at the cumulative risk assessment of pesticides, here we have Now, for the future, implementation of this prioritization methodology using monitoring data for different population subgroups and target organs. So a preliminary analysis for 375 pesticides retained for prioritization, a probability screening assessment for each single pesticide, again using this cutoff value of 10% of the health-based guidance value to retain the compound for the next step. Organ screening, create assessment groups by target organ, probabilistic assessment for each organ, and then, of course, put it all together within a scientific report listing the pesticides and the organs that require the cumulative risk assessment. With that, I would like to give you some conclusion and future perspectives. I've presented earlier on this morning the mixed stocks guidance document, which provides harmonized guidance for risk assessment of multiple chemicals in frameworks for each risk assessment step and reporting tables. I've presented then the scientific criteria for grouping, the guidance document, which will ought to be published hopefully by the end of this year. We had a public consultation started in May. We are now putting it together to publish the document. Finally, some experience with the pesticide residues from colleagues in the pesticide unit. Here, they're working a lot towards faster implementation and cooperation with member states organizations to perform this cumulative risk assessment. And a few thoughts on the future work in this area, including the use of new approach methodologies for the risk assessment of mixtures. Dealing with interactions, I've highlighted a couple of examples, either use of biologically based models or looking at meta-analysis of human data to use magnitude of interaction in the risk assessment process. Generically speaking, the development of physiological-based model and other biological-based models will be something that we will need to work on more for the future. And we have also an example on dealing with not only multiple chemicals, but also multiple stresses in bees, which is the must-be opinion, which was published in May 2021. And with this, I would like to thank you for your attention and your interest, and I'd be happy to answer any questions you may have. Thank you.
好了，那么我们第一位演讲人的这个全部的这个演讲已经结束了。那么因为时间的关系的话，我们就先不提问题了。如果大家有问题的话，可以
don't ask questions right now, and later after the meeting, and you could ask for the speaker's contact information to ask questions via email. And then the third speaker is already online.
Hello. Hello.
Hello.
Okay.
It's
我们第三个演讲者是来自丹麦技术大学的Christine Nellemann 博士。那么我想的话，现在就可以Dr. Christine 开始她的报告。好，谢谢。
Thank you so much. Hello, thank you so much, and thank you for me being able to be here like this. And I'm sorry that I'm not there in person. I used to be that. Let me share my slides with you. And this is going to be another presentation on. I just have to put it in presentation mode here. Yeah, another presentation on mixture effects, right? I'm going to focus on the science behind risk assessments, but of course I think I might repeat some of the things you already heard from the two other speakers this morning, or three other speakers. I'm Christine Nellemann. I'm director of the National Food Institute in Denmark. So here we do a lot of research, and then we advise the Danish government regarding a lot of different things, including mixture of chemicals. So we know we have around 40,000 chemicals in use in the world, but we only have safety information on around 1,000 of these chemicals. And this is actually one of the big challenges and the problem we face. So there's work enough to do for all of us as I see it. When we look into, scientists have looked into what is actually some of the major problems we see, how people have affected the world. We know this climate change, ocean acidification, a lot of other things. Here we have the globe, the green square or round circle here, is where it's okay. And when it's exceeding in red, like the biodiversity crisis, climate change exceeding the green round circle here, we know that we've actually reached the limit and gone above that. But for chemical pollution, we actually do not know. So we have not quantified how it's actually affecting the globe and how far are we into the boundaries that we could get. So here's a lot of knowledge is needed. And this was scientists going together in a nature publication. So how do chemicals affect human health? In Denmark, we know that about 8% of our children are actually made artificially in the lab and then inserted into the womb of women. We know that very many young men get testis cancer. We have several percent of male boys born with mild infections. And we know that this can not only be caused by genetic changes because it's happened quite fast, these changes. So we know that something in the environment is affecting reproductive health in Denmark and in Danish men especially. But we don't know what environmental effects, but we speculate that chemicals and pollutants could actually be part of this. Obesity epidemic we are seeing all over the world, also in Denmark. And what we know is, of course, that if we eat too much, if we exercise too little, we do get obese. But actually, this cannot account for all the obesity we are seeing and the increase in obesity we are seeing. So here we are worried that chemicals have also affected the health of the human population. So then what to do about it? And as you heard a lot about this morning, how to assess the risk of chemicals, we have to know how high is the exposure, and we must know what is the safe dose. So we take exposure over safe dose, and then we look into whether the exposure exceeds the safe dose, is more than 1 in this equation. And then we have to know what the limit values are for each chemical, and how much can we then allow in food, cosmetic, toys, etc. The working environment, like we just heard of. Because as human beings, we're actually exposed to many chemicals a day. It's small amounts, thank God, but both from our food we eat, the water we drink, all the electronics and our working environment, the clothes we wear, the cosmetic products, but also just normal sanitizers. All that is going to have some chemical impact on us. So the question is, when it's too much, and what should we do with it, and how should we add this together? So we know that chemical cocktails are a regulatory challenge, and this is also why it's so great that you have this session here at this great conference. So in 2011, as you can see down here, I'll try to show my mouse. It came out from several of the advising groups here that at present, risk assessments on the combined effects of chemicals in a mixture not commonly carried out nor required by most EU regulations. As you can hear, both pesticides and bio regulators are now within this regulation, but still it's something that is not covered in all regulations. And the regulatory gaps, you can see here up here, we have increasing risk, and there's a level where we see potential concern, and below this level there's no concern. And normally we evaluate each chemical at a time, right? We take one chemical and say, well, there's no concerns with the exposure and the effect of this chemical. But when we add it up, and normally we do see additive effects, the mixture effect could actually be of potential concern. And also here we have, like, from toys we could get some of these chemicals, from cosmetics, indoor air, food, medicine, and emissions and waste environment, and what is then the mixture risk. This is across regulatory boundaries or things how we normally evaluate this, and this is why we need to go into one substance, one assessment across these regulatory areas. So, as you heard about, mixture risk assessment starts with assessing the single chemicals and then making a hazard quotient. So we take all these, sum them up together for the single chemicals, and if it's above one, then there's a potential risk, and we need to investigate that further. And here's what you saw, and you heard a lot about this and how it's done, and examples of it, so that was very nice. So exposure level, of course, on the top here in the equation, and then the safety limit could be very many different, right? TDIs, ADIs, whatever is available. And then the cutoff for the hazard index is by default 1. Okay, so how do we do that? What do we sum up together? So grouping of chemicals, and we'll be doing a lot of science to look into this. So we can do it on adverse outcome, like the liver toxicity we just saw, kidney toxicity. It can also be done on chemical structures, use of, for example, QSAR modeling, quantitative structure activity relationships. We're doing a lot of that as well. Have an open toolbox for these things at our websites. And the hypothesis is that the same structure gives around activity. So you can get some information about the activity that you could group apart. And then there's about mechanisms, mode of actions, and I'm coming to that as well. Whether it's experimental or computational tools. But let's start with adverse outcome effects. And what we have been looking very much into is endocrine disrupting. So endocrine disrupting chemicals can be disrupting in several ways. So here we have like the thyroid disruption on your left, which could impair growth and brain development in the young child. And we know of chemicals that can have these effects, right? Brominated, perfluorinated, dioxins, PCBs. So this could be some we would like to add together to see whether it could be thyroid disrupting. Fertility and malformations can be formed by estrogenic compounds or compounds functioning anti-androgenic. And here we know that pesticides and dioxins and phthalates are anti-androgens. And we know that these over here could act as estrogens. So this could be a good grouping as well, right? Based on the knowledge from the literature and all the science of what the effects the different compounds have. And when we did that on a Danish example with children, and then we looked into, okay, what is the mean exposure level for children in Denmark? And here we could see that for the thyroid disrupting chemicals, it was a lot of the sunscreens actually coming up, because not that we do see that much sun in Denmark, but many is very fairly skinned. So we do need to use a lot of sunscreen. So we saw that on the children, but also PCBs and dioxins and a few of the phthalates and so forth. So the thyroid disrupting was within mostly these chemicals. When we looked into what was the exposure of children of anti-androgenic chemicals, it was a lot from the food. It was the PCBs and dioxins again, the phthalates, and a little bit different here. But those were the main suspects and the main ones we should try to limit the exposure of. Estrogenic chemicals, again here, is sunscreen, but it's also some from food. So this was how we actually tried to look into how to prioritize safeguarding the children a little bit more. So here we have risk of exposure to evaluated chemicals. So we looked into children and we look into the pregnant woman, because unborn children are especially vulnerable, as you might know. And here we looked into for a middle exposure, that's the blue one, and high exposure, that's the red one. And that could be based on different things why some children are highly exposed. But the middle exposure, here we can see the cutoff here, the red line is 1, so the hazard index is 1. So we see the blue one, it is exceeding for the children, the exposure here for the mean exposure, but still it's not that much more than 1. However, for the highly exposed children, we do see that anti-androgenic exposure of chemicals is way too high. So here we would say that the authorities needed to go in and do something to limit this. For the pregnant women and the unborn child, we saw that the mean exposure was below 1 for the hazard index for both anti-androgenic compounds, estrogenic and thyroid disorders, but actually for the highly exposed again, it was way above. So there is something to look into, either to limit the exposure or to make a better grouping and a more specific grouping if it's possible. So that was the adverse outcome when we did it on, for example, endocrine disruptors and on the effect. If we look into the mechanisms and mode of action, and more data is coming here, because as the previous speaker said in the video, it's right that we don't know so much, but data is appearing and there's a lot coming in. And here it could be experimental data or computational tools. So here we tried to do a computational approach to mechanistic and predictive toxicology, and that was back in 2014. So we took chemicals, and here it's 5 pesticides, 4 azoles, and 1 mancozeb here. And we looked into through this computational approach, what proteins do they affect or can affect, and what diseases could that lead to. So when we get this as pictures, we can see here we have the white ones being the pesticides here, prosimidon, tibuconazole, epoxiconazole. Prochloride is actually affecting a lot, or being present in the literature, know that people knows this affects a lot. Maybe this should be more investigated, right? So that's another thing. But we can see that many of these are really steroidogenesis, the production of steroid hormones, estrogen, testosterone, but also the effect on nuclear receptors. We can also see that mancozeb is all here all by itself, so affecting these proteins, but not having any overlap with the other pesticides. So based on this, we should not evaluate mancozeb in a group together with the other pesticides, while we could put these azoles together because they affect some of the same. And we can do the same with disease links. So when we know what proteins is actually affect, we could go and say, okay, then some of these proteins are actually involved in endometrial cancer, in PCO, in virilization, breast neoplasms, and so forth. Here it's more on the spermatogenesis and testicular function over here. So based on many of these areas, we can get the computers to look into all the data we know about these different proteins and see what diseases could then be affected or derived by these effects. So it's a very good way of having overview of very complex data to be able to group chemicals based on mechanisms. And we can look into human targets and diseases, also using all the medical and pharmaceutical literature here, and generate hypotheses on pathways and disease associations with chemicals. But of course, also we have some weaknesses, right? So it depends on the amount of experimental evidence. Like I said, prochloride might be the pesticide best evaluated and investigated, and we need more data on the other pesticides, for example. It's not straightforward to go back and say, okay, this disease showed a link, but how was that? What different proteins made this link? And then the type of association, we can see that it binds to a receptor, for example, but is an agonist to the androgen receptor, working as testosterone, or is it an antagonist? And then experimental validation might prove helpful afterwards. Even though we cannot test all mixtures, we could test some. So here we have it. We have a pregnant woman, and she can be exposed to pesticides, bisphenols, phthalates, dioxins, PCBs. And then what to do? Then we start often grouping them by, is it reproductive toxicology? We're looking into liver toxicology, no toxicology. And this is how we can group the chemicals, right? Like we talked about. And then we look into the hazard index with the different quotients. And if it's below one, no problem. If it's one above one, then we need to go further into it and investigate. So this has come to the prediction of mixture effects that was also talked about in the previous lectures. And this is when effects of the components are known. So we have to know that the components all produce the effect of interest and they don't interfere with each other. That was talk about synergism or how this could act, or antagonism. And here we have only seen that for a few effects in the lab, actually, with animal studies. But still, it's something we should be aware of. We made a very pragmatic mixtures risk assessment tool because we needed it for our risk assessment, and also because we needed data to take both exposure from food, but also from all the other exposures that we know about. So that was what we tried, both in food and environment, and then we put in toxicity data. And it can be found here on chemical mixture calculator .dk at and then you get you are asked for a password, so you can please mail to our professor Anne-Marie Vingård to get the password, and it's free of charge and it's possible to use. Of course, it's something you need to play a little with, but it's the purpose of it is to perform chemical mixture risk assessments and to identify critical fruits and/or chemicals that we should inspect more and evaluate more. And then also changing dietary habits. Right now, people are talking about eating more sustainable, for example, in Denmark. So how does that affect chemical exposure? And these things is actually published just here in 2021. So this is a busy slide, I know. This is how it's actually looking, the chemical mixture calculator. So you go into consumer groups, you can choose adults and children. And if you then add everything together and the exposure in Denmark, you could have a hazard index right above 1. However, we know that probably not everything is important for one of our organs, right? So we should go in here and say, okay, I would like to have an organ system looking into the kidney, liver, thyroid, or how it is. And CAGs are like written here on the right-hand side. It's a cumulative assessment. So it could also be on effect type, like male reproductive development, thyroid histology, and more specific types of things. And then we try to put on the chemical name and so forth. So this should be played with. I know it's a busy slide, but here you get the hazard quotient out here for the single chemicals, and then can be added up for the mixture you would like to evaluate. So, experience with risk assessment in a European Union. As you heard from both EFSA, which is the Food Safety Authority, and BFR, German organization, we do it on pesticide contamination in foods. We do put these exposures together. We look into it also with dioxins and bees, and are actually doing that for some years. And for the first time, actually, we have done it with 4 phthalates, so 4 compounds with effect on male reproductive health. So a phthalate mixture risk assessment was done within the EU. So in 2018, EU abandoned for the first time harmful chemicals because of cocktail effects. And in 2019, 2 years ago, the EU Parliament, that's the politicians, said that there's an increasing evidence showing that endocrine disruptors can work together to produce mixture effects. So this is definitely something that is going to be rolled out to more areas. So how do we design mixture studies, and how do we do it in the lab and in science? So we could take the chemicals and doses selected based on their effect and mode of action. So we predicted maybe that we could see some effects of these chemicals, and then we can add them together and design a mixture containing these model compounds. Also to see whether the mathematical prediction actually show the same in animals or cells or other studies. Or we could do it the other way around, where we do biomonitoring here in big EU research projects, where we do see what is in the blood or urine of chemicals in a pregnant woman or many pregnant women, and then we compose the mixture according to these real life exposure, and then we can mix this and test it in different settings. So this is another thing, and this we actually tried to do. We took human biomonitoring data for 27 chemicals from males and females in the US. I mean, it's the FDA having this on their webpage. So we just took means for blood and urine, and we tested it in animals. And you can see that the compounds are quite different, right? Acrylamide, some DDE, but also some heavy metals like lead and mercury, some perfluorinated compounds, and different things. And this was published in 2016. And when we try to look into, so we had controls, rats here that were not exposed to the chemicals. We had low dose exposure to these 27 chemicals, and we had mid dose going above the human level, right, of exposure. And we did see imbalances in hormones actually, because you can see something happens in these animals, at least in the time frame where they were exposed. We did see something on toxicokinetics, some liver toxicity, and changes in the metabolome. So it is important that we go in and have a look how chemicals are affecting humans. And also we published this in current opinion in toxicology in how we do the hazard mixture assessment. And you have already seen this from some of the other speakers, but it is again a busy slide, so I'll just go through it slowly. So we start up here. Do we have toxicity data, ADIs, TDIs, and can we set a reference dose? And if we say yes here, then we can calculate the hazard quotient for each compound, like I said, exposure or over the reference dose. And if it's below 1, then are there any expected deviations from dose addition, whether it's synergism or others? And we say no. Then we can do the hazard index calculations. So put them all together, all known effects and mechanisms. And if it's below 1, other chemicals or sources that we should think of, the working environment, other things. If no, then we have no risk identified. But of course, if we do not have the data available, then could we estimate exposure available? Could we do something else? No, then it's not possible to do this mixture evaluation, right? But if we could, then we go back here. If we have a hazard quotient for some of the single compounds above 1, then a possible risk is already identified. If we had something more than dose addition, then we should do a case-by-case mixture risk assessment, etc., etc. And here we come to the grouping. When we put them all together, we have a hazard index above 1. Then we group into in vivo effects or alternative data. And again, if that still is above 1, then we have identified a possible risk. So it looks busy, but it's actually quite useful when you get into using it. So the take-home message here is from me also, that mixture effects are seen at no observed adverse effect levels for single chemicals. And that means that one chemical at a time underestimates the risk. The risk at high-end human exposure in some cases we see, and that we can also actually predict mixture effects based on single compounds, the effect of single compounds, and that's why we should always try to do this. So thank you so much for listening, and I hope you got it all through to you. Thank you.
Thank you, Dr. Christine. 我们看看现场有没有问题，我们可以有一个问题来向
From the floor.
没有问题 Okay, no
Like,
question. Thank you again for your presentation, Dr. Christine. 那么我们上半场的这个报告就结束了，我们现在进行茶歇，然后3:50我们准时开始我们下半场的报告。下半场的报告的话，主要是由我们国内的几个专家来进行介绍。好，谢谢大家。 那不是要报备吗？好了，时间已经到了，我们下午的下半场，3点50准时开始。那下半场的话，第一位的报告人是来自复旦大学公共卫生学院的施卫东教授。因为疫情的原因，他也是不能到我们现场来参会。那么他采用这个线上。
Of the COVID-19, he couldn't manage to come here, and he will introduce the mixture exposure assessment research in his lab. Mr. Xu, are you online? Okay, and Mr. Xu, please go ahead with your presentation. Thank you. Distinguished
我今天报告的
gentlemen, my topic today is real-world mixtures of
副产物，它的
infection byproducts in drinking water exceed their additive individual genotoxic effects even at low concentrations. I'm from Fudan University, the public health lab. Nitrosamine were designated as a probable human carcinogens by IARC. Mainly, it came from
除了工业过程以外呢，
it
它
says that
常常发现在以氯胺消毒的饮水中出现的消毒副产物里边。
it
食品中的nitrosamine 呢，主要来
detected either in drinking water or foods.
污染的食物。第二个方面是在水源水受到污染以后，这种化学物质不能被有效的
polluted water
在氯胺消毒
source
中呢，进一步形成了 nitrosamine
and insufficient disinfection, and then further nitrosamine
特殊消毒副产物的水进行
would
食品
occur.
过程中，使得
Then in food processing,
化学物呢就和
nitrosamine
机体。那么同时
enters into human body,
也会产生少量的这种化学物质，我们把它称
and then it will generate chemicals
整个
inside human body. Nitrosamine exposure came from 3 parts in the contaminated foods.
采用氯化消毒的饮水。第三个呢，实际上是内源性的这一部分，
Water
但是情况下在研究
And then the
考虑。那么 nitrosamine 这种化合物
human body.
我们
Nitrosamine
常见的有9种这个化合物，它主要包括了
have
NDPA、
9
NDPHRA
commonly
但是
seen
饮水里
factors,
化合物呢，通常是几种
but
共存的，
the
而食品受
usually multiple chemicals exist in drinking water. Nitrosamine
或者是几种。那么
in
为了探讨这种
water is only one form of the chemical, and in order to identify the impacts on human
那么最佳的方式呢，实际上是
chemical exposure, and actually the drinking water is the main source because
比较清楚。第三呢，实际上讲
in it is very effective, and also we could follow up and track the chemical for a long time
污染的类型的不同和食品加工
according to different contaminations and food processing methods.
在这个食品
We
和
could
这个中间过程里面，能够准确的确定暴露量的 nitrosamine 进行研究。
confirm the exposure
那么
between the
nitrosamine
process.
化合物为什么
Nitrosamine
这是因为在
is
绝大多数
ignored.
情况下它的剂量水平
What
低，
are the reasons?
往往
Because it's
10
low
大克
dosage,
10大克
usually in dozens of
很少有在饮水中超过1微。
nanogram.
那么按照
It can never reach the level of milligram. In 48 countries, cities,
在中国一些传统的
drinking water can be detected with nitrosamine.
严重的地区以及饮水污染严重的地区
Highly
可以检查出 nitrosamine 这种化合物，它的暴露总量
nitrosamine
是美国的3到5倍。 那么因此，
exposure
如果我
can be 3 to 5 times of that in the United States.
那么另外一个方面是来自于消毒
Polluted
过程
water and then from the disinfection process. Nitrosamine
主要是来自于单一化就高剂量的毒理学，传统的毒理学，
single high dose
人类
toxicological studies.
的混合物。因此，
Actually, the
如何去考虑这种
exposure are mainly the mixtures of nitrosamine.
乃至未来所关注的一个重要的问题。
So
遗传毒性是在健康风险评估中
the
优
genotoxicity is a priority concern for the human risk assessment of foods.
也就是高于环境
Use
剂量
single high dose
数百万倍的剂量进行染毒。目前现有我们有关 nitrosamine 的致癌效应的研究，绝大多数
to in the
来自
research or risk assessment. Usually, we use the
剂量的数百万倍进行
animal exposure level
实际上暴露
in the risk assessment, but actually
数百大克至数微克
it is different from human exposure.
也
Usually, it is dozens of or
在人体的暴露水平
gram exposure. So in human body,
影响的时候呢，那么我们
the
要在准确的了解其暴露评估的
impacts to understand it, we need to
的分析。那么
analyze the
我们
hazard
思考了
level.
简单的办法，也就是以
We think maybe we can do it in a simple way.
的
That is the actual exposure nitrosamine,
为基础，
the concentration or the types of mixture,
在健康风险
the real exposure in human in health assessment.
的时候，
Usually we use the
进行
or thousands
不
of
因
factor
也是借助于它以现实暴露
of
水平
certainty factor.
100倍到1000倍来作为染毒浓度。
Consider the 100th or 1000th times of the actual exposure as a reference,
它的遗传毒性的时候，我们希
so
望
that we could get the genome
低剂量和暴露的作用模式，同时呢，
ecological effect.
遗传毒性
In the process, the
稀释分子线和关键的物质，以期望要形成以机制为基础的机
we
制
want to form a mechanism-based risk assessment that is from MA to MOA to AOP mode.
从而来提升风险评估的准确性和可靠性。那么
Ability and
化学中的水
accuracy of assessment. The nitrosamine
现实暴露水平，我们分别检测了原水
by
以及出厂水的过程，以出厂水的
source water or factory water.
染毒的剂量设置为依据，而细胞毒性呢
Use it as a
CCP8这种试剂盒，在观察了
basis
物质
of
在异物质的作用，
contaminated level.
就是模拟污染物的现实组成
We
和它
simulate the formation of pollutant.
我们
So in
重点的测试方法，它分别考虑了基因的水
quality
水平，即采用
level, and we would use M4.
微核实验。也，这个胞质组织微核实验是一个体内实验，而同时呢，我们也观察了 DNA 损伤及其基因损伤的可
And
能。
also
实验 SDGE 实验，也和
we use SGE
检测伽马 HRAX 以确定它的。
experiment to test gamma
那么
2X.
模拟水中现实组分的
And then the GCMS was employed to detect
它这
nitrosamine from drinking water, and the genotoxicity assay was conducted by CCK8.
用那个氧化应激可能
The
是
previous research
这种化学物诱导遗传毒性的
believes
我们也观察了这种化学物对氧化应激的生物标志物的影响，同时
and we also consider its
抗氧化
impact to NRF2 pathway were assessed in order to confirm whether this effect
的 biomarker 通过改变氧化应激的这个分子生物标志物引起的，我们
through changing the biological factor, we also use the antioxidant to prove the
through key events, we can do evaluation. Based on that, we have considered the human exposure risk assessment. We consider the carcinogenic risk and a non-carcinogenic risk. We consider HQ number, HQ value, and also HI value, which is hazardous index and quantity. So the exposure of nitrosamines in finished drinking water, the
实际上是从40
is around 30 to 30, while NDMA is around NEMA is around 20. So most countries do not have the regulations regarding NDMA. Only California and in US have NDMA limit around 10 nanogram per liter or 9 nanogram per liter. So the current finished drinking water is 2 to 3 times of the standard of California state standard.
那么，当我们采用细胞毒性测试的时候，一方面有2方面的，一方面是观察这种混合暴露的细胞毒性，同时
toxicity of single nitrosamine and their mixture have G2 cell. If we want to save 50% of cell survival, these results provide us important reference from laboratory. It shows that 3 pollutants, when it is lower than MD 50, it lowers MD 50, while it maintains 70% of the cell viability. The joint
那么，为了探讨它对基因
stronger than the single toxicity.
突变的影响呢，我们以鼠伤寒沙门氏
And
TA98 和 TA100
based on the mixed exposure to mixture of NM increased, we also tested the mutagenic potency. So it means that it can have
9的存在的条件下呢，它要到1000倍的时候才可以引起
to the 1000 times they will generate the
提示这种化合物呢，需要在代谢的情况下才能引起它的致突变性增强。因此，我们把
it will happen under the scenario on the condition of metabolism. So we call it in
那么，为了探讨这种化合物它是否能够引起基因的损伤呢，我们采用了卫星试验，也就是通过
we also used
测定 DNA 的伪
laboratory test to test the DNA double strand break and the damage
了解它的双链
to
基因双链断裂的情况。结果我们发现了，在混合暴露的时候，
see
在
the
1000
double
倍的时候
strand
呢，
breaks and
在
damage
1000倍的混合暴露，
when the exposure is around
明显的
1000
增
times.
加它的DNA 的双链断裂的损伤。同时呢，它也引
The
起了
breaks and the damages
gamma
of
HRAX
DNA
的
double
水
strand
平的显著
increase
增加。那么
around
提示了这个混合暴露的
So it means that the
exposure
mixture exposure is more severe than the single exposure. So we tested
它
the
对细胞对 Hepatitis 2细胞所产生的 ROS 的影响。我们结果我们发现，
RS in mixed exposure and single exposure cases, in 100 times mixture exposure, it have a severe impact on the RS mainstream. And we also find out that it can generate I'll also find out the mixture exposures change the GSH and the SOD and MDA level of hepatitis cell. And in the case of 100 times of real life exposure, and this is a really strong oxidation process. And in traditional toxic study, the dose is actually is like 100,000 times to a million times different with each other. So to verify this kind of sequencing, we monitored exposure to NAMS mixture, activated the NRF.
抗氧化和适应性反应通路中呢，它的一系
So
列
in
蛋白
this NRF2 pathway,
1100倍、10倍的就可以引起 NRF2 的开始表达发生改变。到
7 times or 100 times when the density increase, it will
三胱氨酸的它的 GCLM 的表达水平呢，在1倍的时候就进行表达。
but
那么
the
提示，
expressions of NRF2 and related proteins
而在XO1 的
now
时候，
after mixed exposure to nitrosamines was increased rapidly, which shows that the mixture exposure of this chemical
下游的抗氧化酶和二项解毒酶的一个显著性的改变，那么提示
will have a significant influence on the upstream protein.
它激活了机体的抗
And they also
以保持
activate
一个正常的
the
状况。
NRF2 pathway.
我们为了验证
Based on that, to verify our
天
idea, we use
NAC， 那么这时候呢，我们
NAC.
观察了细胞对
We
染疫
monitored
观察的几个
the cell damage and
形成率，第二个是核质芽的形成率，
we
第三个
consider the
桥的形成率。在这些众多的观察里面，我们发现这种混合暴露，第一方面呢，就是说在天然抗氧化剂都显著性的降低了各自
when NAC
维和率、核质芽和核质桥率，而在这个过程呢，天然的，而混合暴露的这种混合暴露的效应呢，就是天然化合物的NAC 呢也能够
the NAC for mixture exposure will also change the different rate in those four tables.
这种混合暴露的认为呢，这种混合暴露的
So we can conclude that
超过了它的单独作用的组合，因此
the mixture exposure
认为呢，这个 nitrosamine 这种化合物
mixed exposure is more severe than the single exposure.
那么在此基础上呢，我们进行了致癌的风险评估。
Based on that, we have done the assessment on AMs based on the concentration in the real world in terms of carcinogenic risks of NAMs. I think in the non-carcinogenic risks,
与现行的标准距离相差的很大，因此
I think the last different is quite different with the others.
评价方式
So if you use traditional way of HI, we cannot determine the
是属于可以接受的。
carcinogenic
通常我们认为
because
值的话是以1为值，以大于1或者小于1来
because we will use
那么我们现有的如果用 HI 指数来
those
做的时
more
候，
than one,
符合现有规定，认为它
Right.
没有风险。然而我们在遗
it
传
means that it's risk-free.
已经发现到了它
But through carcinogenic risk analysis, we find out the value is more than 1.
有害效应比较明确的这种
So for those chemical mixture exposure, we should consider
作用的波动
the target point,
大大的增强。因此，
and it will increase the sensibility
即使是在低剂量范围里边的
even if in low
那么它
doses.
可能如果用传统的方法说，它可能会忽视掉
In traditional method,
那么
it will still generate differences. So based on that,
有关 nitrosamine 这种化合物的暴露源呢，实际上是一种
The-
工业源，也就是说，我们
actually
现实中
the
这种
general toxicity exposed to NAMs,
是它是
some of them come from real life,
上游污染来形成的。
from the
在
upstream.
过程中，虽然原始中存在的一部分污染物
Although the
可以
drinking water
处理去除，但是在这个
will be improved in terms of the quality,
内高的氨氮，还有含有大量的有机前体物。那么这种情况下，如果采用氯胺消毒的时候呢，
if we use
加重
the
nitrosamine
chemicals, it will also increase the nitrosamine's toxicity.
nitrosamine 这种化合物里，
Nitrosamine
通常情况下，在中国的饮水几乎
in China's drinking water condition, we can test ND in 48 cities and also an NDMA in many cities in China, and around in 40 cities, in 80 cities it can be tested as NEPA. So in real life simulation, we find out these kind of a risk assessment can be used in other city, in many cities, not only in China. And also we use test tools in other cases. For different endpoint, we can use the general toxicity test can be conducted by multi-endpoint assays demonstrated. And we have tested gamma HAIX and find out that we find out the very subtle changes to find out the damages of DNA double chain. We also used intro test and because AG laboratory are quite ultra test because of time is quite limited when with its obvious effect. But the general toxicity is quite high. We can use intro test to verify these above mentioned tests, and we find out that in single exposure doses, the three chemicals will increase. The real-world mixture of NAMs exceeded their addictive individual genotoxic effects, and we use natural oxidative to stress, and also we combine with NAC to find out that then whether this genotoxic property could be by oxidative. By doing that, based on this response, the SOD change and the GS SCGE change and CBMS change is a series of important events in the reactions. We hope use this kind of a reaction to find out the toxicity pathway. And we can also, based on ROS, GSH, MBA, and NRF, well, if these chemicals do not express, we want to make sure the density effect in low dose expression.
On this basis, we assess
我们又评估了它的HQ 和 HR。那么
HQ and H2
它往往可能会影响到，如果用传统的方式评价，它往往会低估了它的风险。
In case of traditional method, the risk can be underestimated. So our research
奶超次品化合物联合暴露的超过了它自身
and combined exposure of multiple chemicals
具有非常重要的作用。而按照现有的暴露水平，根据暴露水平和人群的
according to the exposure level at present, as in drinking water, the CDI, on the basis of a reference value is calculated with HQ, and then the
在现有条件是高于美国 EPA 的暴露水平的。那么同时呢，我们
the carcinogenetic risk is higher than the American level. So the carcinogenic risk of assessment is higher than the acceptable level.
一种源在现实的过程中里面，我们还会从食物里面暴露出 NDMA 和其他的污染物。但是
So in the future, the genotoxicity exposed to mixture of assessment cannot be neglected. Both drinking water and food exposure cannot be ignored, and this is the preliminary result of our research. And finally, thank MIT, CIFSQ, Conference Organized Committee, and National Key Special Project on Food Safety of Science and Technology of People's Republic of China, and our partners and long-term partners for the great support and cooperation in the past. Thank you.
谢谢曲老师。我们看看。
Thank you, Professor Chu. Any question from the
有一些时间可以提一个问题。
conference room? We have time for one question.
好，那如果没有问题的话，好。
曲教授您好，
Professor Chu, I'm from the Food Safety Assessment Center. Just now you mentioned about the assessment need to consider the water source and the food exposure, all the risks combined. And also you compared it with the EPA. In their cumulative effect, did they consider both the water and food? Thank you. This is a very good question. EPA considered drinking water a single exposure. It didn't provide any health guidance, but only considered the industrial pollutants in drinking water. The NDMA in water after 2015, and they found this substance is generated in disinfection. So American EPA only took the drinking water into account. Thank you, Professor Xu. For more questions, please ask him after the meeting. And next, we are going to invite the second speaker of the second session, Mr. Qian Yongzhong, Professor and Director of Institute of Quality Standard and Test Technology of Agro Products, Chinese Academy of Agriculture Science. And he will make the presentation online. Good afternoon, everybody. I'm from Chinese Academy of Agriculture Science. Thank you for the invitation and the moderation of Mr. Li. Very happy to share with you the research progress on combined toxicity evaluation of contaminant mixtures in fresh food. And first, I would like to share with you our achievements by our team, and also I want to explore the difficulties and challenges in this field. My presentation covers 4 aspects. First is background and situation. Second, research we focus on. Third, achievements and progress. And fourth, bottlenecks and
这个领域当中目前发展的一些瓶颈与面临的一些挑战。首先，我想简单的说一下这个
First,
背景。
I will cover the background and situation. As we all know, the industrial materials and the pesticide and fungicides, everything increased rapidly. Every minute, the chemicals used
研发以及与使用对我们的
more
生态
than 10, and which cause
在政府和社会各界的共同关注和努力之下，
the government and the whole society in
好的方面去进步。我们鲜活
situation and the single chemical
也极大的降低，但是我们同时也特别关注
is reduced, but multiple pesticides, environmental pollutants,
跨类
and
现象，
some other types of pollutants coexist.
都不超标，
And only a single substance
可能存在的
doesn't
拮抗
go beyond the acceptable level, but the combined effect will cause adverse effect on human health. Some
通过不同的途径，主要是经膳食暴露途径
and
来
then the
释放。
food exposure is the main source.
一种是暴露于同一化合物的聚集性暴露效应，另外一种是暴露于多种
Effect to single chemical and the cumulative effect exposure to multiple chemicals. Both of the exposures are concerned by the whole international community.
多种农药共存的现象，可以更
The combined toxicity
鸡尾酒效应
can be described as the cocktail effect because there are different types of registered pesticides and the repeated
效应存在的
use of them result in the cocktail effect
效应等类型，以及对不同宿主产生的效应强
and then the intensity of different
头中尾发现，同
multiple
特别是跨
chemicals or combination
联合效应强
will result in different intensity and different results. And then the mechanism is unknown to us.
共暴
And then the co-exposure
那么当前的田间农药方式以及绝大残留现象标准，是否可以有效主控这样的
and whether we could prevent such kind of cumulative effects
依然是监管的难点。
difficulty in regulation. So based on the reality,
安全骤引发专
the
中国农业科技创新工程以及国家自然科学基金
programs by the National Natural Science Fund and some other program,
我们是以
we studied on the mechanism and the interaction of combined toxicity effect, and then we studied on the methods and techniques of combined toxicity effect evaluation, and then we
新农药组付费使用
conducted the research in combined risk assessment of typical pesticides in fresh food. We want to address the following problems, including the screening, the common
机制组具体分
allergen and grouping
针对具有
chemicals.
争夺联合效应的农药组提出混合
And
原则，
provide a solution, possible solution in managing pesticide, and also provide some reference to the plant quarantine. And these are the results achieved in recent years. Based on lipidomics, we screen the targets of imidacloprid plus acetamiprid on cell lines.
共检出率相对突出，
Some typical occurrence pesticide
水平下，联合毒性效应表征的规
and
律，
try to find the patterns so that we could find the common sensitive
机制。比如，
substance, for
姜
example,
黄、小白菜、芹菜、草莓、
strawberry,
果树产品中，
celery, the pesty residue
组合比重
with high residue,
这种组合
and
都是新
the combination are from the same pesticide.
烟碱
And for
乙酰胆碱受体激动剂同乙酰胆碱受体选择性结合，导致昆
the
中枢神经阻断或异常，
nerve disruption and death can be caused
Layer2A， 并基于
and based on the neutral fat and the target
从指责代谢角度
methods so that we could prevent the effect or the
在
functioning
IC2 低
of
不
some
暴露体
substances.
胞内甘油磷脂、鞘磷脂及谷胱甘肽代谢
And
可被显著结合。
this effect, and for the further study through further screening, and then the
这说明
fat level
比丛林和
can also be increased so that
氧化还原态失衡，同时
the cell structure can be changed, and also
造成
which may result in death,
所以我
etc.
们建议这种同样的
We
子弹有点大宗果树以及
also assess the rice, peanuts,
共检出率较高的
and
新农药组合
found
进行了筛选和研究，
over 20
发
combinations
现多菌灵
based
在
on
100
the
组
untargeted and
代
targeted
谢
lipidomics, the types and quantities of differential
联合代谢的代谢干扰
metabolites induced by combined exposure were higher than those induced by single
在蔬菜、
exposure.
茶叶、中
In
产品上被记录，
vegetable
但可用于水稻、玉米、花生等
cannot
作物的病虫害
it
防治。
can be used for the pest control, and then the result,
与多菌灵辅配后，
and
可提
so
高药
we could improve the
研究我们发
effect.
现这种过表
The combination could
先胆碱脂质过表达，从而
result
破坏
in the overexpression and damage the cell membrane.
其次，我们采用了模式生物巴马鱼的模型，并
Based
基于
on the zebrafish model, this typical combination showed more synergistic effects on reproductive and development
多菌
toxicity,
加毒素比重
more significant
在较
than
大
neurotoxicity.
不同剂量组合
So in different doses, it
系统
will show some
大家可以看到
synergetic
以下
effects,
我们也发现
combined
这种
effects.
组合可能
So
通过
such
排解性
kind of a
信息的效应
combination
甲状腺
showed
分泌来发挥
synergy
效果
through IL-17 signaling pathway and thyroid secretion and acetylcholine.
另外
And
根据我
also
的分析
based on the meta-analysis and TDA software and adverse outcome pathway AOP of
流体有害结晶
carbon
该路径涉及多菌灵可能通过与
toxicity
维管蛋白结合，诱导
constructed. And then they are damage to the reproductive system and deformation or even
汇报，主要
death
就是目
of
前我们在不同的农药组合联合性
children.
方面研究
So
的一些初步结果。
these are the preliminary results
研究
we
这些效应的
obtained
同时，我们
in
在关注
analyzing the combined effect, and also we developed some
在
models
联合效应评价方法探索
in
与
the
模型优化方面，
exploration and the optimization of a model. We
联合效应评价方法及手
used the combination of no effect concentration. We simulate the and predict binary and multiple
生鲜农产品中主要农药残留联合风险。
for the combined risks of a fresh vegetable. We conducted some studies.
是基于草甘膦、
done as
乙草胺
SD and
等
PAR and 46 of chemicals
多种非线性函数
the zebrafish, and we collected the toxicity sensitivity, and we
多元组合的无作用浓度模
and
型。
predict binary and multiple combination of no effect concentration. And this kind of model actually have get more accurate results. Based on that, we have specific teams working on PNEC software. This model actually can be used in different chemicals, mostly used in zebrafish, and it can be used in
效应的风险评价。
environmental safety. Apart from that, our team's study also have evaluated risk accuracy of oral, low dose, and subchronic co-exposure to multiple pollutants.
基于独立作用 AI 模式下开发的总概率 ORP 基础上，
Risk probability model based on AI model framework combined with probability assessment strategy, and we have developed the IOPR model. In this, we have conducted the calculated the value of long.
的准确度。该模型
This model is used for collecting, assessing the health condition of a human body.
同时依据 OECD、
CD, US EPA, and other,
RPF 法，采用了历年针对不同先
we
锋
have used we have collected the acute and chronic cumulative exposure risk of 19 organ non-ferrous peptide in different populations in China. We find out that vegetables have the top ranking vegetables are celery and Christmasium. In fresh fruit, those
风险研究方面，
the pesticide combined used in spinach and pear. We collected
即允许复配
the chemicals. There are over 100 chemicals, and we looked into over 20 chemicals residue in vegetables. We also follow closely that we use this widely used chemicals and with highly detection rate, and also these chemicals are the qualifier are prohibited in Europe and the US. We find out in spinach, the dimethyl and above the allowed level for human body, and it's three chemicals combined together. The half-life expiry also increased sharply, so we do not recommend using those chemicals, those three types of chemicals. What a mixture of these three used in plants and vegetables. From our study, we also find that in cabbages, dimethyl 4 and plus acetaminophen plus cypermethrin, and also these types of pesticide combination used in coffee. Also, we used in combination the dimethylmorph and carbon diazine can degrade below the MRL value within 14 days, and a safe interval of 14 days is recommended. For cucumber, we also look into the pesticide recommendation. Furan, chlorpyrifos, and also the pesticide combination in lecture. When using combination, every pesticide could be degraded to their MRI value within 7 days. The recommended safe is lower than the average. And we also look into the carbon diazine plus combination in different products, mostly in ledge, in apple, strawberry, peach, and also in apple. We find out the residue is the combined residue is higher than the single residue. So we think this is a high ranking risk. So from this table of risks, we can find out that the will sharply increase the residue risk. And I think this should be catch your attention. In order to see based on zebrafish and cell, the combined toxic effect intensity of 25 typical pesticide combination in 11 fruits and vegetables were determined. 12 pesticide combination synergistic effect and the multiplier of toxicity was 6.3 to 6. And I believe this result will provide reference for the future pesticide production and the use in real life. That is my presentation of our team's work in the last few years in major pesticide combination and this mechanism and how we can provide suggestions in our real life production and life. So later on, I would like to present the applicability of methods. But I think today many experts have the similar idea that in terms of applicability of method, we food and its pollutant source, and I think it is long-term chronic exposure in low doses. And because of the food source is quite verified and the diversity of a different population, the assessment method need more study in terms of applicability. Now we use the CUA model. This model's scenario is quite limited in handling, in trilamine, and pollutants in similar chemicals. But our progress is still quite limited. And second discovery is that we find out we have an increasing demand of toxic and dietary exposure data, and also the field drug registration data. New chemicals developed and used while we do not have the following up data, and that will make it even more difficult for us to evaluate the isolation of data quality and the coupling between data and the evaluation method have constituted barriers to promoting joint effect evaluation and application. We need support, regulatory and administrative involvement. Last but not least, we find out the global because different governments have different understanding regarding combined use of chemicals, and there are also gaps from different governments, and that is because they're increasing of urgency of resources sharing and the capability. US and the European Union actually have worked a lot with obvious results, and we find out that in terms of data sharing, there are still barriers, including regulation, monitoring, and the system framework. We still need more sharing of these resources, not only in China, but for countries like US and the European Union, who are the front runner in research. We still need to share more with each other to tackle the mutual challenges. But for China, we have been working on the combination of pesticide. And for example, we have done the accumulated risk assessment, and which has been sponsored with support science and technology. And the administrative department from China in this regard, the Ministry of Agriculture, also provides support for us. And we have drafted the basic guideline for accumulated risk assessment. And based in China education, we have data regarding report. We have produced report in different regards, and we're going to add more data into this report, and we're going to submit this report to Ministry of Agriculture for review. And that these kind of reports will act as reference for future policy making and the next step of R&D work. In the end, I would like to thank the Ministry of Science and Technology and the Ministry of Agriculture, and also China Academy of Agricultural Science for their support. I also would like to thank different parties for involving in the R&D process. For time interest, I cannot go into details to share with you. If you are interested, feel free to contact me through my email. My team and myself will talk to you in more detail. Thank you for listening, and thank you all. I'd like to thank the host for the session. Thank you, Mr. Chen. If you have any questions, please contact Mr. Chen through his email. Next, we'd like to invite the next speaker, a colleague of mine, Madam Song Yan from China National Center of Food Safety Risk Management Risk Assessment. Let's give the floor to Madam Song Yan.
All
the experts, colleagues, good afternoon. I would also like to discuss on the topic of cumulative risk assessment. So in our center, led by Mr. Liu, we have done our study and research, and also discover and exploration in terms of model in cumulative risk assessment. We also joined the Mr. Qian in the 13th five-year plan, and we have continued our research. Actually, the path of a risk assessment roadmap is quite rapid. We start from 1983 framework of a risk assessment. Until now, we have a science based on hazard, based on epidemiology, exposure science, and toxicology. Assessment has also been developing. I also want to tap on that we have introduced, we have translated a book called 21st Century and application in risk assessment, which is recommended by WHO. The aim of publishing this book is that we want to publicize the technology and the methodology of this book in China. So back in 2009, in the food security law, it is mentioned that we're going to develop a risk assessment methodology.
风险评估中心呢，就这么就给大家一个侧面了。我们评估中心呢，其实也是依据国际的总体的国际的方法和指南呢。
Also follow the international guidelines and the methodology we have built our own.
So we set up our own methodology. Currently, our methods have been used in the risk management, in hazard assessment, exposure.
目前呢，也是积累了很多的这个。
We have developed different methods. For example, in hazard
以及这个基于这个我们的一个
proposed alternative testing for screening common effects and high concern toxicity and points and W.
我们这个毒理学这个数据非常的重要。
As our approaches, and just now the toxicological method is very important. We develop
非测试的方法，比如说 QSA 的
and for the QSA or the cross-reference and TTC method
技术的开发
development and researches. In the exposure assessment, we carried out China total diet study, and the moderator will provide a
监测的技术以及我们
monitoring and external internal exposure exploration approaches. And
在这个风险表征方面，我想我们
holistic exposure approaches are studied on, and also these are the methods or researches in the methodologies we have conducted. Why we carried out such cumulative assessment works or methodologies? It is because we really need them, and because we are exposed to different substances, and the regulatory body also need some relevant information. And the EPA proposed the concept of
其实风险评估呢取得了
in the past 3 decades, it experienced rapid development. In
一个风险评估它的一个方法和策略。
WHO
这几年呢，他们也是在不断推进
combined exposures to multiple chemicals, and they promoted the method and to promote the harmonization across the world. In 2019 and 2021, EFSA proposed the guidance for this cumulative assessment and the grouping of chemicals. Though the guidance is still
这个方法，但是呢，它其实是给我们提供了一个很
provides a very good way of thinking, an idea.
暴露风险评估的这么一个会议
made a meeting about the cumulative assessment for the multiple
一个实现的这个国际的
over this method
协调一致呢，更像
harmonization or actually was proceeded forward with all these activities and events. Cumulative assessment report, the international community use the decision tree and the decision framework. And the speakers also talked about their risk frameworks. We analyzed the cumulative assessment frameworks of different countries and proposed ours. Strategy and methodology framework. The framework consists of 4 parts, and then the problem formulation, and hazard assessment, and the risk characterization. From top-down method, and we started simple and gradually. Of course, for each tier, we provided the methodology and data required by the cumulative assessment. And then large amount of substances need to be assessed, and how to assess them by types, that is, how to group the chemicals. It is considered to be the precondition of the cumulative assessment. And EFSA, Mr. Jin introduced the tiering framework, which provide us an idea or concept in grouping, and they use the to integrate all the available data, and tier by tier. In tier 1, the MOA and AOP is considered as the criteria for grouping. If the substances have a common MOA or AOP, they can be grouped together. Here I want to stress is from external to internal to the target organ, and this is the toxical dynamics, and then the target molecule changes actually will initiate the molecular event, and then the key event, and then finally result in the adverse outcome. And from molecule to outcome, this is what we call toxicokinetics. And we cannot only consider TK or TD, but both of them need to be considered together. So this is the strongest evidence for grouping. In assessment of a chemical, actually there are only few chemicals with toxicology evidence. So currently the better method or new method is the NAMS. Effectively provide the toxicology information. Currently, the methods include the in vitro evidence and the genetic or TKTBV models. All these methods can be used for analysis, so that we can tell the toxicology properties of a substance, but different institutions consider different things in grouping, and we need to consider the whether all the chemicals are under the same management model. For example, different pesticide, food additives, etc. Different institutions or regulatory bodies are responsible for them. So in the risk management, and the terms of reference can be different, and many experts may say if the chemicals can be
但是我个人来讲呢，可能
from
这种
regulatory bodies. Maybe it can be practical, but I think it will work for the
这种就是之间的这种实
post
际。
market. We need to consider the actual exposure.
那么我们假如说这个物质分到了一组以后，我们要考
And
虑的第二个问题就是啊，进入这一组的化学物质
after grouping, and the second thing we need to consider is prioritization and whether all the chemicals need to be assessed with exposure. So
目前从方法学来说呢，
we
现
need to
在
consider the priority. Currently, we have two methods. First is the exposure-driven approach, and
就危害驱动的方法
two
呢，包括
methods.
WHO 以及 JCFA 呢，都提出了这样一个阈值，就
And
说
the threshold are proposed by EFSA, FAO, WHO, and JACFA. If the exposure reached more than 10 of the
评估，如果说它低于呢，就不需要了。另外呢 ，EFSA 也提出来一个，就是说呢，
assessed, if it's lower than 2, we don't need it. And EFSA would consider the 10%
优先，如果
of
低于
single
呢，
chemical
就不用考虑。
combined risk.
也听到 BFR 的专家也提
And
到，
DIR expert
5%或者是1%这种可能性啊。
value can be variables. For example, 1% or 10%. For
刚
example,
好比那个阈值呢稍微低
the
那么一点。
substances are slightly lower than the threshold.
全部就排除出去了。这时候我们要
Not all of them can.
降低阈值，最后呢让
We need to lower the threshold
最后保留的这个化学物的它的这个风险呢，它能够达到
to
总的风险的90%以上。
keep the remaining substances threshold to 90%. So actually we need to consider the combined exposure, the possibility of it, so that we could get the information about exposure. For example, the exposure source and the use of the substance and the exposure period, whether prenatal or pathway, the physical and chemical properties, and the fate properties, magnitude, frequency, and duration of exposure, and the specific target population, for example, the smokers, source use patterns, and life cycle of exposure, etc.
这里边呢，我想给大家举两个，就是关于这个
Two examples about the exposure-driven approach.
一个是选的是这个添加剂， 另
The
外
additive, and another one is a pesticide. Additive sources of data are from
这个数据叫全球的新的
GNPD, and this is the food additive data in global new products database, which is commonly used in the risk assessment. Another one is our monitoring data of pesticide. We
array 这种计算的方法，
use frequent item set mining and to calculate the binaural substance or to binary,
出现的频次以及相对它的一个支持度。
that is the repeated occurrence.
想给大家展示的就是我们关于
Here
添加剂
is the
指标呢，就是食品添加剂的组合的一个个数啊，2元，
and then binary
一直到20多个
to more than 20.
这个纵坐标呢，就是相当于它出现的这个
Here the frequency is also shown, and also the different foods are
呢，我们的加工食品里边
result shows that processed food
4点多，
without additive account for 4.4%. 102 are 17% and 77%. Altogether, the foods with additives reached more than 90%. So actually, we are also
其实我们只是展示了这个前3位，其实在
the exposure-driven approach for multiple chemicals, actually different combinations and may have different frequency of occurrence and also different types of
2元、3元以及 n 元的。
And for example, sweetener, it can be used for a single time or more than one time, etc.
使用呢进行了一个分析。
These are also analyzed.
这个我想展示的就是关于
Through this slide, I want to show about pesticide
个数啊，然后这个
types of a pesticide and the frequency of a pesticide, and also different types of vegetables. We can find out that 43% of vegetables in China contain at least 2 or 2 more pesticide residue. And for different combinations, we also use analysis into that. We find out in combination of at least two pesticides, there are still risks, safety risks. This is the quite in alignment with the results from European Union. Also find out that from among all the most common 2 combination to 10 combination,
其实我想通过这2个数据
is often used in combination with other pesticide. And I want to say that in real life, the combination of pesticide is quite universal. And in our risk assessment, we can it could undermine the actual risk if we only assess a single pesticide and in the dose setting and also refer to our study. I want to take a look at the combined effect of
相互作用啊，这个剂量相
there are like subtitles or synonyms and observed effect
的和，而效应相加呢，就是说它这
while the interactive or synergy interactive can be divided into synergy and another one. And the judgment of the type of a chemical combination, which way can we use? Actually, there is no unique standards in the international society. The very common way is ISO graphic procedure and mixture toxicity index method. These are 2 commonly available methods. And I mentioned about risk hazard assessment. Secondly is about exposure assessment. In terms of exposure assessment, we can use the models. For CIFSQ models are the most frequently applied, in which the total response corresponds to the sum of all the individual concentrations multiplied with their respective potencies. So CIFSQ model-based mixture assessment tools, we will assume that here I present very common models, including cumulative risk index, point of departure index,
HI 的方法是最不用
relative potency.
今天我们大家也看到前面的几位报告人在讲方法的时候，大多数用的都是
potency factors. Many previous speakers used the HI method.
这里边展示的就是关于我们的这个剂量相加的这个模型。
Here
这张我想左边给大家主要
on this slide, on the left, it is target toxicity dose based HITTD model, which is mentioned earlier. And on the right side is the interaction based on HI model. The interaction, it's a default weighting factors for the modified weight of evidence. Through this model, we can better understand the interaction on the accumulated exposure. Here, I would like to show you 2 examples. The first is the hazard.
生性添加剂，我们这个采用的是一个
is used in HI model. On the left,
结果。右面展示的我们是
risk individual distribution of most commonly used quaternary addictive combination.
的时候，我含量的数据啊是用的是
This theoretical exposure assessment,
按标准最大的容许
if this chemical is used along the exposure
因为
level,
大家在实际过程中不可能用到那么高的
will
量
be higher.
一般
And in real life, the actual exposure assessment, we will use a little bit less amount. They depend on the techniques needed. And we will calculate the amount of exposure which is different. From the chart on the left, we can find out it's 4 food additives.
我们看一下，假如说是我
And
4
the
元啊，我只是
for
用
food
它
additives,
考虑它的分析，
if we consider the risks individually,
的人可能存在
around
一个健康风险。
5.5% of population exposed to
一个累积暴露评估的时候，我发现呢有
addictives were combined, then they are around 4 13.69% of people are exposed to health risks. And if these addictives are used alone, there is only 0.02% of people exposed to risks. While combined use, the risk rate would be 0.04%. So we can say that the results were similar for all 4 sweeteners, and the 4 additives were twice as risky as when used together as when used alone.
通过一个就是我们的一个相对效能因子的方法来进行，然后相对效能因子的方法，我们可以看到，如果
On this
单独考虑每一种酒精
assessment, if we consider every additives were peptide alone, only 15 people are exposed to risks exposure. And for case 2, we use another model. We want to use RPF model of peptide. We find out that we choose a certain subject, and we use that as a target chemical, and other substance we use the comparison between other chemicals, and all substance we collect the number of BMD and NOAEL, and at a very exact dosage, and we change the dosage to the target.
暴露量，然后呢，这时候我们发现有
We find out that over 400 people are exposed to risks, and
所以呢，目前呢，我们是用大量的数据来
varies
对我
in different cases. So for different models, the accuracy and the efficacy are also verified. We have established the interface and the platform for you to better operate. This is the new NAMS method, which is mentioned earlier by Mr. Qian. I won't repeat myself.
其实就是这么多年进行累积风险暴露评估的这些方法的这个研究，我
As
想
I've been working
里面来说还是很难的。
believe it is quite difficult compared with other sectors. We have
不断的去研究和解决的。
constant effort and constant research. I also want to say that in this interaction or combination, we still need more data for that. So we need to collect more data in this regard. And for NAMS method, for QSAR, and we can refer to TTC, in silico, TKTD, PBTK, and high throughput toxicokinetics model. And we also can leverage machine learning, which are really good method. And through this weighted method, we can better analyze it, and we can better understand the toxicology. So I think this methodology would be the focus of our future study. And also about the cumulative risk assessment, we have the biggest challenge for us is data gaps. because many data are generated from ultravital, from food, from our dietary, but for intro data,
所以我觉得我们应该就是去
data. So we need to collect those bio data in our bio sample.
这些方面的信息。另外针对MO
For MOA and LOP is quite important because
分组的一个金标准啊，所以我
is a more accurate example for us to group. And
其实在这个就是相关的这些中
for grouping.
多，所以在这个管理方面，指南的制定以及
So the formulation of a guideline and standards is still needed.
去投入更多的精力去做这方面的一个研究。另外，对于优先级方面的考虑呢，我想有一个是
hazard-driven and exposure-driven approach for the prioritization of multiple chemicals should be taken into account. I think the step threshold value is quite important, but still we have some problems. In terms of the threshold value, we need more data to determine which threshold value is more suitable, and it will be more conducive for alignment in international society. I think the toxicological data gap were quite important. It's really difficult. We cannot do the animal test or animal experiment.
就是累积风险评估来说呢是非常重要的。我就觉得这些
specifications. When we're doing experiment, I think we could collect and fill up the data gap. For time interest, I would like to conclude here. I'd like to thank Mr. Song from our team, and also like to thank Mr. Tong from Tongji University and Mr. Chen's team, and also the colleagues from our center. I believe you have invested a lot of time and energy into this research. This is my contact. If you're interested, feel free to contact me. Thank you for listening.
谢谢松燕的报告。
Thank you, Madam Song. If we have questions, we could ask this question to Madam Song. Thank you, Madam Song. This is the very first time I listened to the presentation. My question is, in your case, you assessed around dozens of chemicals. You have adverse outcome, very common adverse outcome. In your study, have you ever considered additives together with pesticide and test the assessment for multiple or combined exposure? I think the question is a very good question because we only analyzed additives for pesticide separately. It is up to the current available data. Based on the data, for one types of pesticide, for example, pesticide for apple or for spinach, the data actually will only use the spinach to test a certain specific pesticide, but I'm sure we can use this type of spinach to test other chemicals. For example, heavy metal. We still have this data gap. We need such kind of a data, and we need the assessment in different risk and hazardous factors. So I think your question is a plan. Your question is mentioned in the 15th five-year plan. We will collecting data in the future. like you mentioned, we will collect data from different sectors, or we'll do experiments using different types of additives or pesticide. If I think it's easier for us to consider only pesticide or chemicals, but it's not enough for us to get diversified data. Thank you for your question.
还有其他问题吗？好，那没有其他问题的话，我们再次感谢。
To continue with our schedule, thank you, Madam.
那今天最后一个报告。
The last presentation will be made by me. I would like to introduce a program under the 13th five-year plan. Most of the presentations talk about the cumulative effective assessment, but our research mainly focuses on the exposure assessment.
我们刚才我介绍的这个项目的名字叫食品污染物暴露族解析和总筛研究。
Is under the title of characterizing exposure of food contamination in Chinese total diet study. And I would like to introduce the results of the exposure assessment. First, the overview of our project, so that you could understand better about the function of this research. And through the total diet study and human biomonitoring, that is the external and internal exposure, we are trying to identify the models and the methodologies to address the contaminant exposure. In our research, in task 1, the dietary exposure assessment of the traditional and emerging pollutions of Chinese main food will be updated. We conducted 6 times of the total diet research, and our main research is from the task 1. The task 2 is about the biomonitoring, which focuses the exposure in the early days of life, and that is the breast milk monitoring, so that we could get the POPs in China. In task 3, the bioaccessibility of POPs, heavy metals and their forms, and perchlorate in food will be investigated to make a more accurate dietary exposure assessment. The substance released from foods, how much of them can be absorbed by human, and how much could be removed or lost in the process. And the task 4 is to set up the PPDK model for 25 typical food pollutants, and which was introduced by Ms. Song Yan just now. And then with the PPDK, the external and internal exposures can be combined, and then the epidemic research and the relationship with doses can be derived with the external exposure, the health value. In task 5, we consider the risk factor and the metabolite characterization, and so that we could warn the risks of pollutants in human body. And task 4 is based on the BMD research, the dose effect relationship for dioxins, cadmium perchlorate, BFRs, and PFAS will be explored based on epidemiological study to propose benchmark dose for those pollutants. Actually, the HBM data with EU-wide coverage is also carried out in the program. Currently, they have a human monitoring is sponsored by the EUDP and European Commission, and they need to explore the relationship between external and internal exposures so that they could identify the source of exposure and provide information for the exposure risk reduction. And finally, it will provide the relationship between chemical exposure and health. And usually we target at a single chemical, but in the actual scenario, it is often a mixture exposure. The mixture exposure of a single pollutant and multiple pollutants. Last year, I introduced the epidemiological research-based health effect with mixture exposure and some identification of a key element. This time, we mainly focus on the talk about the cocktail effect. That is the more toxic with multiple chemicals. That is different substances can generate toxic, not 1 + 1 = 2, but more than 2. Actually, when they enter the human body as a mixture, it will cause more adverse effects to human health. And how do scientists assess chemical mixtures? And actually, this topic has been mentioned or focused on by different speakers, and the EFSA method and EPA method, etc. I will not go into details here. We use two hypotheses. First is the dose addition. Dose addition means that individual chemicals in the mixture have a similar toxicity, and the doses are added up and combined with exposure for the cells for the assessment. And PFAS in EU is used in the mixture exposure assessment. Another one is response addition. We need to consider the independent toxic effect and also the integrated effect. Actually, a very good case is REC and RECB. The toxicity is assessed in this way, and dioxin and dioxin-like compounds, 29 congeners. And for the mixture assessment and the total exposures, concentration is multiplied by the toxic factors, and then the equivalent can be used. Actually, this is the addition of different toxicities. The exposure assessment for group PFAS based on China TDS. TDS is widely used in industry and several products in our lab. We would consider the TDS as a PFOA And these are the substances widely existing in human body, environment, and foods, and the detection rate are the highest. And they are concerned by people. Currently, they are listed as a POPs convention. In many countries, they are prohibited in production. As such substances are concerned by the whole society, and the mixture assessment is also put high on the agenda in different organizations and countries. The different health-based guidance values are used, and because different methods are used in different organizations, so the health values are different. And EFSA has stricter value, and this is is calculated by week, by day, or by month. So based on the theory, EU proposed the group PFAS guidance value. Actually, far higher requirement than that in the past. And the China TDS used data from the 6th TDS. We started since 1996. 6 TDS has been conducted, and 24 provinces are covered. 86.5% population are covered. Actually, the representativeness is very good. Our objective is to estimate the dietary intakes of chemical contaminants and some nutrients by the residents in China, monitor the trends of chemical contamination in local diets, provide scientific data for specific food safety risk assessment projects, and development of food safety regulations and standards. Also, it identifies the priority pollutants for national food surveillance by using non-target screening method. And this is the procedure of TDS, the dietary survey, so that we could get the food consumption, and the sample list will be used for sampling. After sampling, and the TDS is different from the pollutant assessment, so we will refer to the cooking habits and preparation to reflect the pollutant.
它的这个含量是会发生变化的，有些是会减少，那么也有些
The pollutants quantity can be changed, and some increased, some decreased. So through the sample testing, and we could get the occurrence of pollutants, and then with the analysis, we could get the exposure data. Actually, 13 categories of food are tested. In PFAS, we consider only 9 of them. For assessment, we adopted 2 methods. First is a single point deterministic estimate, and we use the standard people's consumption in different provinces. That is the adult male with moderate physical works and 63 kilograms by weight. And finally, we got the mean
同时也采用的这个概率评估的方法，在我们
estimate, and mainly the pollutant data is used the mixture of food.
这个个体的这个食物的这个
because for individual food analysis.
这个很难承受，因为我们用的是4万多个个体的消费量。
We used over 40,000 individual consumption data.
测的话，那么这个成本是
to use
难以承受。目前，所以的话，我们实际上
individual data for their assessment. So in the exposure assessment, the weight is individual weight.
And based on the gender and the age group, we also find out distribution of potential dietary exposure for Chinese population and subgroups. According to the PFAS, it include C4, C10, PFC, precursor, and also alternatives. And then the mainstream is SPE, LC, MC, MC.
结果从检测结果来看的话，在我
From
们
the results, we can find out that the PFAS is detected in meats, and the detection rate is much higher than that of vegetable products. And also among meat, the aquatic food and meat has really high number. And for Europe, the number is dominated in terms of PFOS and PFOA. But for PFNA and PFHS, the intensity is relatively low. In terms of concentration of groups, we find out that the
是高于谷类和蔬菜，然后是薯类和水果。我们也可以看
legumes actually has the highest number in
差异也是比较大。
it has variation of the different groups.
那么通过点评估的话，我们获得了我们国家不同省份
Some deterministic estimate mean dietary exposure for Chinese male adult, a number for PFOA in Beijing and Shanxi has surpassed the threshold laid out in by European Union. For PFOS, the province of Heilongjiang has intake much higher
高于IFSA 的这个
rates, which is also higher than the guidance from IFSA.
美国和这个澳新的健康指导值的话，
And based on US and Australia and New Zealand, our exposure is lower than their.
那么再看一下这个混合暴露情况，那么把这
Let's
四
take a look at the combined
新的这个健康指导值的
the IFSA's latest number. Certain provinces actually has high exposure risks. For PFOA and PFOS, they contribute a big portion. But there are two exceptions, Jiangxi and Jiangsu. They have really high concentration. Maybe there are specific contaminating pollutants. We need to further look into it. For PFOA, for medium level to P19.5, which they are all lower than the guideline from Europe. And for some group, for PFOS, it's the same story. Around 3% to 4% of the population surpassed the threshold of PFOS by IFSA. For PFAS, for group PFAS, based on IFSA 20
出的这个group PFAS 的这个健康指导来讲的话，
guideline
这个人群超标的就超过这个健康指导值的人群的就比例就会比较高，达到了%。
The IFSA is much higher to around 32%.
从 P75开始就已经超过了
since
欧盟的这个新的健康指导值。
5, that is much higher than the EU IFSAS average. Based on different the probabilistic estimate distribution of potential dietary exposure of Chinese population subgroups by gender and by age. They we find out that for adolescents aged between 13 and 17, we find out males exposure is higher than the female, while from the charts below we can find out
暴露水平的话是有一个比较明显的差别的。那么通过我们的概率评估的话，我们还可以获得不同这个暴露水平。
Realistic estimate can find out that the contribution to group PIFSA dietary exposure. We can find that exposure
水产、肉啊、蛋，它的这个
food, eggs and meat.
但是不同的这个暴露的这个暴露水平的话，它是还是
levels of exposure has different amount. We can let's take a look at lowest ranking exposure, which is aqua food accounts for very small amount, but in senior age group, the aqua food exposure has more exposure. So we should look specific into a certain types of food, and based on different age group, that difference is not so big, so obvious, and we still differentiate each other on different types of food source. We also compare their comparison
一个混合暴露的一个暴露情况。
PFAS between China and the EU. We have two different methods of assessment. We are relying on probabilistic assessment while EU adopts the signing value. We also have different testing results. In China, assigning value is for LOD, and for the original food plant original food value is 0. In the mid-level, citizens in
要明显的低于欧盟的
has lower exposure compared with European number, but for high exposure group,
欧洲的目前的暴露水平的话，差
smaller gaps between Europe.
这么一个差别。那么小结一下我们的这个
Rice,
研究结果吧。
our current research.
我们的这个研究发现，
Based on our study, we find out PFAS contamination in food with there is a mixture of PFAS contamination in food with animal food being significantly more contaminated than plant food. Among the group PFAS of concern, PFOS and PFOA remain the main substance of contamination, and the median weekly
中位数是2.28个纳克每公斤体重。
PFAS in the whole population of China's TDS was 2.28
从整个人群来讲的话
per kilogram body weight based on a probabilistic assessment.
摄入量要明显高于成年人。
population had a weekly dietary intake of group PFAS that exceeded the latest TDS.
不大。
While dietary intake was significantly higher in the lower age groups and in the adult and the elder age group.
总体上水产、肉类和蛋类是 PFAS
The concentration of each food group varies significantly with the total exposure level. Overall, fish, meat, and eggs were the main source of PFAS intake, but the contribution of cereal and vegetables could not be ignored. There was little variation between sex and age group. when comparing median intake, Chinese residents have significantly lower intake of PFAS than the European residents. However, for highly exposed population, the difference between China and the EU is not significant. It's not significant and not essentially at the same level. So for the future, I think we need more rational and harmonized approach for evaluating the health effects of combined exposure and the corresponding health-based guideline values.
那么这样的话，如果
The risk assessment include more emerging perfluoroalkyl compounds based on nationwide population biomonitoring, such as 6-2-CI PFAS in China is needed.
现在我们关注的 PFOS，虽然 PFOS 和 PFOA，
Although PFOS and PFOA are the dominating chemicals in terms of intensity, but it's better regulated and there are more alternatives.
这些这样 F53B 它这种拟件氮替代以后的一些
So I think there are better alternatives, and the results show that the exposure level is
就是 PFOS， 它是 PFOS 的一种替代物。
higher than PFOS. It is actually the alternative for PFOS, but the exposure risk is much higher, so we should include those new alternatives into our report. And different countries and regions should, based on their own food monitoring results, to find out the combination and or different types of exposure, or determine which methodology should be used. That's so much for my presentation. Thank you for listening.
大家有什么问题可以提一下。那如果没有的话，我今天的报告也就完了。那么同时的话，我们这个分会场的
Thanks so much for our session.
非常感谢大家。
Thank you all for coming
这个分会场的这么
to the discussion.
活动吧。那么我们也希望在明年
I also hope to see you next year
这个分会场，或者说整个的我们
in our session or in this
不再
conference.
受我们这个疫情的干扰。
I hope next year we will be free of pandemic and we could have face-to-face interaction with all our speakers and our audience,
能够到现场
and
来
also
参加
could
会议。谢谢大家。
I could see you offline. Thank you.